right, next up we have Jacob McNamara from Caltech, who's going to tell us about the conserved charges of closed universes.
Great. So first of all, let me say thank you to the organizers. I'm really enjoying this conference. I think it's good to have these discussions and arguments. So this talk is very much in the spirit of Daniel's talk in that I'm going to try to define what it would mean to have a global symmetry in quantum gravity to tell you, what it is we say can't exist. So the starting point is to discuss what are the actual physically meaningful things you can compute in a quantum theory of gravity. So the sort of observables or quantities that you can compute are things like space-time amplitudes. So these are processes by which we fix some boundary of space-time, say in the past and the future, and we do something like a gravitational path integral over the space-time in between. So this could be in the context of ADS-CFT, and if you want to be conservative, maybe my whole talk is in the context of ADS-CFT. These could be scri plus and scri minus for computing an S matrix. Maybe more controversially, they could even be something like the world line of an observer. But in general, what we do is we fix some part of the geometry and we integrate over the rest. So these space-time amplitudes are well adapted to the notion of conserved charge. I think we're going to hear later about difficulties in defining topological operators. But the notion of conserved charge makes perfectly good sense in this context of these space-time amplitudes. So a conserved charge is just any selection rule on these space-time amplitudes. Now, we want to talk about global symmetries. Gauge symmetries are fine in quantum gravity. So a symmetry is global if and only if the charge, the conserved charge, can be non-zero in a closed spatial slice, like here. We heard about that also in Daniel's talk, that gauge charges are ones which can only be defined with a non-trivial boundary. And if you can define a non-zero charge in a closed slice, then it's a global charge, otherwise known in this context as a baby universe. So the general goal of my talk is I want to make some comments about how to think about conserved charges. And by the end, I'm eventually going to ramp up in technicality and describe some new work, giving what I think is a complete description of the possible conserved charges in a gravitational path integral. So the first comment to make is that conserved charges can be understood as an obstruction to factorization. So for example, if we have a space-time amplitude that has some charge flowing through it from the past to the future, well, maybe that amplitude is non-zero. But the amplitude where we have charge just coming out, or the amplitude where we have charge just going in, would both be zero by charge conservation. So any charge corresponds, a global zero-form charge corresponds to a violation of factorization of space-time amplitudes into something just in the future, something just in the past. And so from this perspective, global charges are obviously incompatible with the holographic principle. So the holographic principle would tell us that the locality of the holographic dual, so the space-time amplitudes in the holographic dual are just the partition function of the dual CFT, and they would factorize if your boundary is disconnected. So from this perspective, I think no global symmetries is obvious in some sense in a holographic quantum gravity. And I want to emphasize that really the statement of no global symmetries is only something you should expect to be true in a UV complete theory, in a theory that has black hole microstates. It's not something that I think you should expect to be true semi-classically. So on that note, I want to make a couple comments about what I think are some common maybe misconceptions. So the first is that I want to claim that wormholes do not break symmetries. Wormholes certainly have something to do with violation of symmetry. But let's consider the following process. Let's consider a space-time amplitude where in the future we have a disconnected universe. In the past we have a disconnected universe. And at some intermediate time, some charge is carried from one to the other by a Euclidean wormhole. Now, from the perspective of an observer in this universe, it looks like there's some violation of charge. But from a formal perspective, there's no violation of conservation of charge. The charge has moved within the system. And in some sense, this is not so different from having, say, two pieces of metal. You put them next to each other, an electron goes from one to the other. The total charge is conserved. It just has moved. If you want to use wormholes to conclude that there are no global symmetries, you need to, at some point, input UV completeness. So you could do this in a variety of ways. You could assume the validity of the replica trick, and you could say these are two copies of the system, and I'm computing the square of the charge violation. This is an assumption, and it's true, should be true in a UV complete theory, but generally, semi-classically, it doesn't have to be true. You could input factorization. You could assume that you're able to unitarily integrate out wormholes. You could assume the quantum extremal surface formula.
So if I was an effective field theorist on the left-hand side, probably would write an effective field theory with some coupling data which violates the selection rule charge. Right?
Yes. So what I would say is that in quantum gravity, the validity of your ability to use the rules of effective field theory to correctly compute quantities in the UV complete theory is a UV-sensitive problem. Right? Generically, if you integrate out wormholes, you're not going to get a local quantum field theory. I would say for more comments in this direction, not specifically about symmetries, I'll point you to these two papers of Akers, Engelhardt, and Harlow-Shakulian. These two papers, I think, sort of outline how I think about the role wormholes play in quantum gravity. Now, I should have said that wormholes do not break invertible symmetries. And part of the reason I'm being so pedantic is that wormholes do break non-invertible symmetries. Maybe we shouldn't call them symmetries. Maybe this is a reason we shouldn't call them symmetries. So one way to understand this is that non-invertibility is equivalent. I don't know this as a theorem. I'm pretty sure it's true. Non-invertibility is equivalent to the violation of the selection rules for the symmetry when you put the theory on a non-trivial topology. Non-trivial here meaning not a sphere. To give you an example, consider the non-invertible chiral symmetry of massless QED. The existence of this symmetry corresponds to the fact that there are no abelian instantons on R4. So the chiral charge is conserved on R4. But in a gravitational path integral where you sum over 4 manifolds, the charge will not be conserved because you can have abelian instantons. Now, there's a moral reason why the gravitational path integral violates non-invertible symmetries. And this is going to play an important role throughout my talk. So the fusion of closed universes is abelian. So if I want to consider the charges carried by closed spatial slices, when I fuse them, I put them next to each other, there's no notion of the order in which I've put my universes next to each other. So they commute. And so non-invertibility is the electromagnetic dual of having a non-abelian fusion. And so if your charges fuse in an abelian way, or for experts, symmetric way, then your symmetry is invertible. And so that's sort of the moral reason that's going to be a driving story throughout my talk. Okay, so this was all so far a discussion of zero-form charges. So I want to discuss not just zero-form charges, but I want to discuss higher-form charges. These are charges carried by higher codimension slices of the gravitational path integral. So we saw in codimension 1, the gravitational path integral computes spacetime amplitudes. In codimension 2, the gravitational computes something assigned to a codimension 2 boundary, but rather than computing an amplitude, we can define a Hilbert space. So what I've drawn here, B1 and B2 are supposed to be codimension 2 manifolds. I can use them as the spatial boundary of a Cauchy slice, and I can define the gravitational Hilbert space of quantum gravity quantized with those two boundaries. So a one-form symmetry, a one-form charge, is a selection rule on the ability to have a non-zero multi-boundary Hilbert space. So before, a selection rule was a rule that told you when an amplitude could or could not be non-zero. So here, I'm asking when can a multi-boundary Hilbert space be non-zero? Just as zero-form charges obstruct the factorization of partition functions, one-form charges obstruct the factorization of Hilbert spaces. So for example, it might be that the two-boundary Hilbert space is non-zero, but the one-boundary Hilbert space is 0, and so it doesn't factorize as a tensor product. An example of this, going back to a paper of Daniels, is the electric flux through a spatial wormhole. So if I have in the bulk, I have electromagnetism, but I don't have electric charges, then I can thread my wormhole with electric flux. And while I do have the fluxed wormhole, I don't have one-sided charged microstates. And so that's a one-form symmetry, and it leads to a failure of factorization of Hilbert spaces. So this is meant to motivate the general problem. So in general, the path integral, maybe the semi-classical path integral, of a d+1 dimensional quantum gravity theory computes the following data. So to a closed boundary K manifold, so this is something codimension d minus K, we can compute a higher categorical invariant, a d minus K vector space of bulk states quantized without asymptotics. this is very similar data. I'm saying my quantum gravity theory is in d+1 dimensions because I'm comparing to like holography. So this is very similar data to a quantum field theory in d dimensions, but I don't automatically satisfy factorization. It's not automatic that the output I get for a disconnected boundary factorizes as a product of what I would get on each side. So the goal in this talk, the goal for the rest of this talk, is going to be to quantify the conserved charges of all form degrees for an arbitrary gravitational path integral. I'm going to make some strong assumptions. I'm going to assume two things, essentially. I'm going to assume the finiteness of space-time amplitudes. I'm assuming that I have a gravitational path integral that I can do. It's a ridiculous assumption. If I have a generic higher dimensional gravitational path integral, I don't think any of us believe that you can actually do it. But I'm going to assume that those space-time amplitudes are computable, and I'm going to assume reflection positivity. So this is going to turn out to be a key assumption. Yeah. So a first try at computing, at describing the conserved charges carried by closed universes is what Coleman and I did in a paper from 2019 on cobordism. So we made sort of a obvious observation, which is that if a space-time amplitude is non-zero, then there better be at least one configuration in the path integral that contributes to it. If there's no configuration in the path integral, then that amplitude is obviously zero. So that motivates the following definition. So given asymptotic boundaries, so these are closed manifolds and additionally field configurations of your matter fields, we can group them into what are known as cobordism classes. So we say that M1 is cobordant to M2 if we have a one higher dimensional open manifold. This is something that is part of our gravitational path integral that connects M1 to M2. So this is an equivalence relation. We can group our boundaries into equivalence classes, and they form an abelian group under disjoint union. And this group defines some global symmetry, some global D minus K form symmetry in our quantum gravity theory. The Swampland cobordism conjecture is just the statement of no global symmetries in this context. It's a statement that in a UV complete gravitational path integral, whatever that might be, these cobordism groups defined this way should be zero, because otherwise there's a conserved charge. So let's evaluate how well we've done at quantifying the conserved charges in the gravitational path integral. So
what does this mean? This means that the path integral is only non-zero if the manifolds are cobordant to zero?
So this,
you say
which
K, is that for all K?
I'm saying that this statement should be true for all K in a UV complete theory, because otherwise you would have a global symmetry.
What does it mean? I mean, the cobordism groups are known and non-zero, okay?
So let me give you an example.
It means that if the manifolds that will contribute to non-zero amplitudes have to be cobordant to zero?
So good. So the cobordism, as I defined it, is an equivalence relation on asymptotic boundary conditions of the gravitational path integral modulo bulk configurations. Configurations of quantum gravity, say in string theory, are not all smooth manifolds.
Yeah, you're being pretty loose about what you're integrating over here, right? So
I'm assuming that you've handed me a gravitational path integral and I know what I'm integrating over.
and you know what the boundary of it
And
is.
I know what the boundary conditions are.
But it might involve branes. It might
involve branes, or for example, it might involve orientifold planes.
Yeah, yeah.
Okay, let me ask this: are these cobordism groups that I can look up in a math book?
No, definitely not.
Okay.
It depends how much you know about your
It's
gravitational
not
path
in
integral.
Milner and Stashin.
No.
Okay.
I think that's what the
Non-perturbative
closed
string
field
theory,
configuration stands for.
Yeah.
Well,
Yeah.
hold on. So, for example, if your gravity theory, if your semi-classical gravitational path integral was just a path integral over smooth manifolds with some given structure, then yes, it's the normal ones you could look up in a textbook. But we know
Okay, but
that
those cobordism groups are computed and known to be non-zero. So I'm
and
trying to
that
understand
path
this
integral
thing.
is not UV
So
complete.
sorry.
And that path integral is not UV complete.
Then that tells you something about the brains.
Tell you something about
Yeah, it tells you
have
about
to
what you need
introduce-
to fix it.
Yeah, just introduce new defects so that you trivialize the cobordism group in there.
Yes.
Are these supposed to be Euclidean path integrals?
I'm imagining Euclidean, yes.
Euclidean, and are they supposed to be over infinite amounts of Euclidean time, finite amounts of Euclidean time?
I would say if that makes you more comfortable, yes. But in principle, I don't think it has to be. But sure. Sorry?
You sum over it.
I'm just saying that I have some context where I'm fixing some boundaries of a gravitational path integral and I'm integrating over the bulk. If it makes you more comfortable, you can put the boundaries asymptotically far away, but I think there's been some recent papers on, say, putting a gravitating observer and fixing it as a boundary condition at just finite distance. It's not obvious to me that it doesn't make sense.
Why should that gauge it? Why is that something that...
That's maybe a separate discussion. Let me say then, for this discussion, you can take these to be asymptotic boundaries.
I mean, I don't even know why it's gauge invariant for infinite proper time in general, but...
When we look at the CMB as a gauge invariant,
Sorry?
when we look at the CMB sitting
No.
here in a finite amount of space,
No, it's not.
but we somehow do it.
What?
We do it.
Yeah, I know, and it's tied to our local group of galaxies.
Yeah, I think that's what he's saying.
Yeah.
That makes a gauge invariant.
I didn't mean to get into that discussion.
Sorry, yeah.
Let's say for concreteness that I'm putting my boundaries asymptotically, and then maybe you still have complaints about gauge invariance there, but I think...
You don't mean asymptotically infinite time, you mean at like the boundary of ADS.
Say at the boundary of ADS. Yeah, good. Any more questions? I'm going fast through this because I want to have time to describe the new stuff. So let's evaluate how good a job we've done at quantifying all possible conserved charges in this gravitational path integral. So I think one important benefit of this description is that these cobordism groups are computable. So if you have just smooth manifolds, they're computable, but even if you have fixed singularities, they're still computable because there's a systematic way to adjoin to your smooth manifolds singularities of a prescribed type and compute cobordism groups. So this is something that's been done in a number of works, that there's probably more that I didn't list. And this leads to specific predictions for new defects in well-known theories like, well-known string theories. Again, the argument is that if these defects didn't exist, then that string theory would have a global symmetry, and I think we believe string theory doesn't have global symmetries. So that's a benefit, but a real flaw of this description is that these groups are too classical. They're an invariant of the classical path integral, where I know what my configurations look like. I haven't taken into account superposition of closed universe states, so I'm not thinking about wave functions, I'm just thinking about particular configurations. And I haven't taken into account interference. So you might have a scenario where you have two asymptotic boundaries, and you have non-trivial configurations that contribute to that amplitude, but due to destructive interference, the amplitude might end up being 0 anyway. In that case, you don't want to say that they're dynamically connected. Related to this is the fact that these cobordism groups, as defined, only captures what we would call topological or magnetic charges. These are charges, conserved charges, which are associated to the topology of the field configuration, and not things like shift symmetries, where the state of definite charge is not a particular classical configuration, but a given wave function. So what I'm going to do today, I'm going to try to explain some recent work that remedies these flaws by defining what you might call a quantum cobordism category. So this is a category which gives a complete description of the conserved charges of the gravitational path integral, which is formed by taking classical manifolds, classical boundary conditions, and forming quantum superpositions modulo gravitational gauge constraints. Was there a question? No. So the approach I'm going to take is I'm going to categorify a classic argument of Coleman, Giddings, and Strominger. I would say that the classic story of Coleman, Giddings, and Strominger, which I'll review, gives a complete description of the zero-form charges in quantum gravity. I should say that the one categorical case is work in progress with Zhencheng Wang, and for a gentler presentation, I'll point you to this recorded talk where I went much more slowly. So let's review Coleman, Giddings, and Strominger. So we want to understand the quantum states of closed, or otherwise known as baby universes. So one thing we know is that if we have an asymptotic boundary, it prepares a state in the closed universe Hilbert space. So this allows us to bootstrap the baby universe Hilbert space in a sort of three-step process. I'm going to emphasize these three steps because I'm going to then use the same three steps in the categorical context. So the first is superposition. So I take just formal complex linear combinations of the states prepared by given asymptotic boundaries, and these form some vector space. There's a inner product or a bilinear form on this vector space. This is computed by the gravitational path integral. Again, I'm assuming I can do it, and I can compute an amplitude. And this defines a bilinear form on this pre-Hilbert space. By reflection positivity, this form is positive semi-definite. And so I can form an actual Hilbert space. This is the Hilbert space where I've imposed the gravitational constraint equations. The baby universe Hilbert space is the Cauchy completion of this pre-Hilbert space under the topology induced by this bilinear form.
So wait a second. So is the pre-Hilbert space the free vector
Yes.
space generated by closed D-1 manifolds?
Together with whatever boundary conditions you need to put.
classes,
Yes.
Or diffeomorphism classes of closed D-1 manifolds.
You could do either. If you don't quotient by diffeomorphism, you'll find that the difference between two states prepared by diffeomorphic manifolds are null. And so they're quotiented. So part of the Cauchy completion is quotienting by the space of null states, the states
So
which.
you're taking the free vector space generated by D-1 manifolds, closed D-1 manifolds.
Together with whatever other data you need to put to specify a boundary condition of the path integral. For example, you could have some classical fields, and so you should put that configuration as well. Yeah. Good. So one conceptual comment is that once we've imposed the gravitational gauge constraints, we've quotiented by the space of null states, and we've taken a Cauchy completion, the very quantum state in the baby universe Hilbert space is conserved. So the Wheeler-DeWitt equation is h equals 0. There's no bulk time evolution. Bulk time evolution is pure gauge. So whatever state the baby universe is in, it will remain in that state. This is a symmetry like projection onto the, I don't know what number you said, 49th eigenvalue?
42nd, come on.
42nd, sorry. Yeah, of course.
The answer to
The 42nd eigenvalue. But because the Hamiltonian equals 0, and we don't have dynamical time evolution, once you've projected onto a solution to the Wheeler-DeWitt equation, the quantum state is essentially a conserved charge. Yeah.
But the Wheeler-DeWitt equation is hyperbolic, so there's generally no positive semi-definite bilinear form on the solution space of that equation.
So, good. I'm not super familiar with what happens if you try to do this in, say, four-dimensional gravity. I know that this has been done concretely in low-dimensional toy models. This is related to the assumptions I was making. So the assumptions I was making was finiteness of amplitudes, which is a ridiculous assumption, and reflection positivity.
I mean, if you do it in string theory, it's simply not generically true, right? You have to have very specific backgrounds.
I don't know how to even remotely get close to computing this in string
I thought
theory.
people say you're
No,
not.
I mean string theory as thought of as world-sheet gravity.
Oh, it's thought of as world sheet gravity.
Yeah. Yeah.
There's a positive definite inner product on the physical state of the
Yeah,
string.
only on the physical states and only for certain background CFTs with very strict, you have to
See, less
satisfy
than
the Einstein
26.
equations for the
That's
target
right.
space.
As I said, the assumption I'm making of reflection positivity is telling me that the inner product I get is positive definite. You can ask, what does it take
Yeah,
to get such
so
a positive definite
it
inner product?
generically won't be satisfied.
Well, I think that inner product is probably not the sort of Klein-Gordon type inner product on the Wheeler-DeWitt.
But then the Wheeler-DeWitt equation won't be satisfied.
No, I think you can take the set of states that obey the Wheeler-DeWitt equation,
Yeah.
and you can define whatever inner product you want on that set of states, right? As long as it obeys the rules of an inner product. I don't know. So I think usually people use this thing called group average inner product or something. I don't know. Which is supposed to be positive. If you ask Don Merrill, I don't claim to understand it, but But I think it's not supposed to be equal to the Klein-Gordon inner product, precisely because that one has states of negative 1.
Sometimes it is, sometimes it's not.
Yeah, you know, but yeah.
All right.
What I can say is that in concrete low-dimensional toy models where you can compute the gravitational path integral, you get a positive definite inner product, and you can compute everything I'm saying. In like 4D gravity, I highly doubt you're going to be able to carry out this computation. But those are the assumptions I made, and this is what you can get once you make
But
them.
you're using the inner product where you define the states at boundaries, right?
That's right.
Yeah, so that's different than what Tom is saying, which is you take a state that obeys the Wheeler-DeWitt equation, and then there's a sort of invariant Klein-Gordon inner product, but I think it's not.
Yeah, that's not the same inner product. That's not the same inner product. That's more like the inner product on the
Yeah.
pre.
In this language of group averaging, these states that are defined by boundary conditions in the path integral are more like these co-invariant states.
That's right. That's right.
Okay.
They're not related with states.
Yeah. Okay. Good. Good. So as I was saying, I think this point is more general than a particular framework. The general point is that if you have a state of a quantum state of a closed universe, because time evolution is pure gauge in a closed universe, there's no dynamical time evolution, that state is a conserved charge. So quantifying the conserved charges of closed codimension 1 slices of the path integral is the same as quantifying this Hilbert space. So what is the structure of the baby universe Hilbert space? This is the argument, and maybe a more modern presentation of the argument of Coleman, Giddings, and Strominger. So the baby universe Hilbert space naturally has the structure of a commutative C-star algebra. So the algebra operation is disjoint union. If I have states prepared by one asymptotic boundary and a state prepared by another asymptotic boundary, I define their product as the state prepared by the disjoint union of boundaries. You can argue, using the axioms I gave, that the null states form an ideal, and so the baby universe Hilbert space has the structure of a commutative C-star algebra. Now, what Coleman, Giddings, and Strominger say is that you can simultaneously diagonalize. You have a bunch of operators acting on the Hilbert space that all commute. You can simultaneously diagonalize that action, and you find a basis of what are known as alpha eigenstates. These are states in which multiplication by some additional boundary just multiplies the state by a fixed C number. If you
You're
insert,
saying if I take the free vector space generated by manifolds,
yes,
I work over the complex numbers to make it a star algebra using this,
yes,
and then it's going to satisfy the C-star algebra axiom that the norm squared of A is the norm of AA star.
yes. Under the inner product I defined by the path integral. Yeah. So the upshot, and this is what's been playing a role in a lot of discussions of ensembles appearing in holography, say in JT gravity. What happens if you insert a complete basis of alpha eigenstates inside of a space-time amplitude, you find that the space-time amplitude does not factorize as a product of dual, say, CFT, if we're in ADS CFT, a product of boundary partition functions, but an ensemble average of a product of partition functions. This is just what happens if we insert a complete basis of alpha eigenstates. A more formal way to say this is that what we have is an ensemble average over the spectrum of this C-star algebra. So we have a baby universe Hilbert space. It's an algebra under the operation of disjoint union of manifolds. And I want an algebra map from the baby universe Hilbert space to the complex numbers. That's a way of assigning to each boundary manifold a complex number, call it the partition function, in a way that respects disjoint union and does factorize. So these are the collection of factorizing members of an ensemble, and the recent result is that the generic gravitational path integral computes not a single quantum gravity, single holographic dual, but an ensemble average. So an example of this is in this paper of Merrill and Maxfield. They show that if you take a simple 2D model of topological gravity, you do the path integral, you get a dual ensemble of topological quantum mechanics. Topological quantum mechanics is just a ground state degeneracy, and here the ground state degeneracy is, they show, is Poisson random. So this is the structure of the baby universe Hilbert space. I I would say that the general description of the conserved zero-form charges in quantum gravity, these are the conserved charges of closed codimension 1 slices, is described by this space of alpha parameters.
I have a question.
Yeah.
In string theory, how many alpha values of the alpha parameters are there?
My belief, although again, this is well outside the realm where I can compute, is that there's only one.
Good, I agree.
Yeah. And so this is what I'm going to say. I would say that the absence of global zero-form symmetries is exactly in a one-to-one corresponds with the absence of an ensemble.
Yeah.
And in a UV-complete quantum theory of gravity, the closed universe Hilbert space, as computed in the UV-complete path integral, should be just one-dimensional. In fact, to your comment about the reality of the closed universe Hilbert space,
Yeah.
it shouldn't just be happen to be one-dimensional. It should be canonically trivialized, which gives it a real structure.
Yeah.
Yeah.
So I have a question about, since you're talking about Maroff and Maxfield.
Yeah.
The title of their paper is Transcending the Ensemble,
Yes.
blah, blah, blah.
Yeah.
So, but you're saying that they're arguing for an ensemble interpretation or
So
not?
I don't think they're arguing. So it's an ensemble interpretation of what? I would say that what they show and what has become clear is that a semi-classical gravitational path integral can have an interpretation as an ensemble of theories. When we talk about quantum gravity, say string theory, we usually mean UV-complete quantum gravity. And there, I don't think they are arguing you shouldn't think of a member of the ensemble as what you really mean. Does that answer your question?
No.
No?
We go on.
The point is that what they show is that they compute an ensemble. They're not arguing that that's how we should think about the theory of quantum gravity, say, we live in. In fact, I would call an ensemble, these ensemble holographies not UV complete. Yeah. So one note, and this has been observed in these papers, it probably missed some. If we did have, in our gravitational effective field theory, if we did have an ordinary zero-form group acting as a global symmetry, we can conclude that this group only acts to permute the members of the ensemble. A formal argument is that G acts on the baby universe Hilbert space by algebra homomorphisms, so it acts as a classical symmetry of the space of ensemble parameters. So if you start with a gravitational path integral that has a classic, just a regular zero-form invertible group symmetry, then this group will be realized as a symmetry of the ensemble, not a symmetry of any member of the ensemble. But in general, there's not a description of the conserved charges of closed universes in terms of the action of representations of a group. That's just not the right structure. The right structure is that we have an ensemble of alpha eigenstates. Yeah. Okay. So this is meant to be review. This is, as I consider, well established, but I guess we can debate that. Now I want to, in the last little bit, I want to describe the new stuff. So what I'm going to do, and I apologize for the technicality, what I'm going to do is I'm going to imitate the construction of Coleman, Giddings, and Strominger at the level of higher category theory. I want to describe not just the conserved charges of codimension 1 slices of the path integral, I want to describe at the quantum level, the conserved charges of slices through the gravitational path integral of arbitrary codimension. So we're going to take the same 3 steps. The first step is superposition. So when we want to talk about charges, higher form charges, the right notion of superposition is not linear combination with complex number coefficients. It's linear combination, say, as objects in a category. So what I'm going to define is what I'm going to call the baby universe pre-category, whose K-morphisms are formal direct sums of closed K-manifolds as they appear in the gravitational path integral. And I should say, for experts, I should tensor this with an appropriate universal target D category. So the next step is to compute the overlap. And in the categorical context, the overlap of objects is computed by the space of homomorphisms. And as I said before, this is the thing that's computed by the gravitational path integral. So if I had 2 codimension 2 boundaries, I say that the vector space of homomorphisms from one to the other is the multi-boundary Hilbert space. Yeah.
So in item 1, do you only take direct sum of these manifolds with non-negative integer coefficients?
Really what I want to do is I want to take formal linear combinations whose coefficients are objects of some, say, d-vect, but really it should be a universal target.
previously you used complex numbers.
Previously, I used complex numbers because complex numbers is like the universal. Complex numbers is the vector space. It should be called zero vect is the complex numbers. So the morphisms in this category are quantum superpositions of morphisms from one manifold x1 to another manifold x2. Is not just the set of classical bordisms from x1 to x2, but the category of quantum superpositions of such bordisms. This is just formal quantum superpositions, but we compute these. These can be understood as being computed by the gravitational path integral. And now we need to impose gravitational constraints. Before, what we did is we took some form of Cauchy completion. For those who aren't familiar, I'm not sure I'm going to be able to explain this very well, but the appropriate notion of Cauchy completion in this context is what's known as the higher idempotent completion. This is a construction of Gaiotto and Theo Johnson-Fried. I don't know why I put your first name. But this is a categorical analog of quotienting by null states. It forms it takes all of the objects you have formed and shows how they are built out of building blocks. The construction is that you take this category you started with and you adjoin to it all possible condensations of objects you started with.
When you say quantum superpositions, are they finite superpositions?
That's a good technical question that I don't want to deal with.
Sorry.
It depends on exactly what type of category you want to
norm
construct.
before.
Sorry?
You didn't define the norm when you said you had a C-star algebra.
The norm was the
So are manifold states norm 1?
Are manifold states norm 1? No, not necessarily.
I thought we were taking the free algebra generated by closed, presumably connected. Closed,
No, not necessarily
no, sorry.
connected.
Closed D-1 manifolds, not connected.
Yes, and the inner product is defined as to be the one computed by the path integral.
There's some bilinear, just linear formula.
Yeah. I'm taking that as an assumption that I can do a gravitational path integral and compute this thing.
That's data.
Yeah. In fact, that's all the data I need to start with. All of this higher categorical data can be bootstrapped starting from this. Good. So I form this categorical version of the Cauchy completion, and what I get at the end of the day is a D category. So this D category is a complete description of the conserved charges carried not just by closed slices of codimension 1, but closed slices of any codimension. Maybe something that's worth pointing out is that if you take, well, maybe I'll say the next slide and then I'll say this. So before, when we had the baby universe Hilbert space, the next step was to understand its structure. And the way we understood its structure is that we understood it was an algebra, and then we used some theorems about the structure of commutative C-star algebras. So in this case, we have a baby universe category, and it naturally is a symmetric monoidal category. So it has a fusion, and the fusion is as abelian as possible under the operation of disjoint union. Again, for the same reason as before. And in this context, we can ask, what are alpha eigenstates? So before we saw that alpha eigenstates were points of the spectrum of the algebra. These can be the idea there is that an algebra homomorphism out of the baby universe Hilbert space is an assignment of factorizing partition functions to all possible boundaries. So here, what I should look for is symmetric monoidal functors out of this baby universe category. This is what's known as a fiber functor. And each such symmetric monoidal functor is a specification of a fully local holographic dual. So I'll compare to Christian's talk yesterday. What we saw there is that the specification of a gapped boundary of the bulk specified a particular member of the ensemble, and another description of that gapped boundary is in terms of a fiber functor. So this is a description of the collection of fully local holographic duals contained in this path integral. I realize this is somewhat abstract. I'll hopefully get to some concrete physics punchlines in a slide or two. So the technical result is that just as the baby universe Hilbert space was completely described as an ensemble over a set of alpha eigenstates, the baby universe category is described by an ensemble over what's known as a stack. And I'll explain on my next slide what that is. For experts, the key technical step is that reflection positivity implies that this category has a property known as being Tanakian. Essentially means that all of its objects have integer quantum dimension. So what's a stack? A stack is like a space, but each point has some automorphism group. So when we had an ensemble before, we just had a bunch of points. Each member of that set was representing a particular UV-complete holographic dual. Here, we're also remembering for each particular holographic dual, we're remembering some global symmetry group or higher group. Now, on the boundary in the holographic dual, that's a global symmetry. In the bulk, it's a gauge symmetry. And the conserved charges in this higher category are the conserved charges corresponding to the incompleteness of the spectrum of the bulk theory under this gauge symmetry. And just to prove that this is something you can compute with, if you take the topological model of Merrill and Maxfield, you can show that its baby universe category is an ensemble over this stack. I have a Poisson random ground state degeneracy. It could be 0, 1, 2. And if the ground state degeneracy of my topological quantum mechanics is an integer, then the unitary group of that is a symmetry. And so I have this symmetry group acting as automorphisms. This is a result essentially of Deline and Milne and Henry Maxfield, I believe, independently. So that's the technical result. I've certainly gone off into mathematics. So let me say what the result of this for physics is, and in particular for holography. So I'm claiming that the data computed by the gravitational path integral, in general, is on some sort of ensemble average over this stack of alpha states. So what does that actually mean? So the partition function is just an ensemble average like before, nothing new. The partition function is just a number, there's no category theory, and you just ensemble average it in the way we did before. The Hilbert spaces, and this is something that's been discussed more recently in the context of holography, is Hilbert space factorization. Now, in each alpha sector, we can look at a Hilbert space with some given boundary, and I claim that the states prepared by the gravitational path integral are not all of the states of a UV complete realization of that theory, but only the ones that are group averaged. So we have some symmetry group acting on the holographic dual. We can project our states to other group average. And for example, a two-sided Hilbert space, we could have a two-sided Hilbert space which does not factorize because we projected onto the invariance under a group. So what this means is that the two-sided Hilbert space could have fluxed wormholes where G gauge flux goes through the wormhole, but we don't have one-sided microstates because they've been projected out by the group average.
You violated disjoint additivity.
Yes, I have. But I'm not trying to talk about a UV complete theory here. Yeah. And the result of this machinery is that this is the only obstruction to Hilbert space factorization. Whenever the Hilbert space doesn't factorize, it's because there's a group acting, not a non-invertible symmetry, not something more complicated, just a group, and the states are averaged over the group. This is the sort of 0 categorical and 1 categorical. I have similar comments to make about higher categorical data, but this is the punchline that I think is most relevant for what people have been thinking about recently in holography.
Well, usually I think of Tanakian reconstruction as obtaining a group from the category. Is this,
that's
is that
right.
the group you're talking about?
So this category is multi-tensor. If it had finitely many objects, it would even be multi-fusion. And the one comment I was going to make, but I didn't, is that if you take the identity in this and you look at its endomorphism, endomorphism, endomorphism algebra, d times, you get the baby universe Hilbert space before, which is not simple, right? If you had a finite set of alpha eigenstates, it would be just a direct sum of simple algebras. And so Tanakian reconstruction, as you're probably familiar, would start with a tensor category, and would get ref G.
Right.
So the stack you produce there is BG. Here, because you have a multi-tensor category, you get a bunch of points, and on each of them you have got G. Yeah.
Same G?
Not necessarily. For example, here, it's not the same G. And that's part of why you don't see this group in the ensemble, because G is essentially averaged over. Yeah, washed out by the ensemble. Okay. So let me summarize what I've done. So I have categorified this classic argument of Coleman, Giddings, and Strominger. And I constructed a D category, which gives a complete description of the conserved charges of closed universe states of all form degree at a quantum level, not at the level of just classical configurations, but of wave functions. So this gives a new formulation of this cobordism conjecture at the quantum level, which would say that if I had a UV complete quantum gravity and I could do this calculation, I would find a trivial baby universe category. I would find that it's equivalent to the tensor unit. This is the n-categorical version of saying that the closed universe Hilbert space is one-dimensional. Then, using this Tanakian reconstruction, I've argued that the only possible conserved charges in quantum gravity arise from this categorical ensemble holography. What we have is we have a stack of microscopic theories, and we've averaged them over the stack in this way I've been describing. So this quantifies the failure of factorization in all codimensions. So thank you very much, and happy to take questions or discussion.
In the interest of time, we should probably postpone. Yeah, okay, all right, we can take one.
So the way cobordism conjecture was useful in the past, right, was because you could have this approximation where you can do cobordism use of, let's say, non-vector theory, so on and so forth, and you predict, as you were saying, magnetic states. Is there any way to use this idea to sort of like predict electric states as well? Is there a way to approximate this if you have?
That's a great question. In principle, you absolutely should be able to. Yeah. I haven't done such a calculation.
But what's the thing that I should compute in the effective theory? So suppose I give you free Maxwell and I want to end up
compute this category. And what you find is that there are conserved charges, and then you demand that those charges. I mean, so there's, as you know, there's the sort of lofty version of the cobordism conjecture, which is saying that all configurations are connected, and that includes quantum superpositions as well.
Right.
So you compute this category, and you find its simple objects, say, and then you demand that there are new defects in the quantum gravity theory that break that symmetry, that connect those charges, and trivialize the category when you recompute.
Okay, if there are no more questions now, let's thank you again.